We are here looking at Chapter 3, Lesson 2. The key questions for this lesson are: how have people's ideas of motion changed throughout time? We're going to be taking a look at going all the way back to Aristotle, which is 300 BC. And what is mass, and how does it relate to motion of objects? We saw this in the first lesson, and we want to make sure you understand it, so we're going to hit those concepts again. Let's consider some questions to start us off. Which of the following items would you say are naturally in motion? Smoke, clouds, boulders, airplanes, the earth. Which of these items would you say are naturally in motion? Motion in a circular path is not natural. Natural for planets, or a perfectly natural way for things to move. What do you think? And finally, what causes objects to move? A. Some things are naturally in motion, whereas other things must be pushed. B. Everything in motion must be pushed. What do you think? Consider your answers to these questions. We are in school, and so when school's in session, we always want to know, what are the right answers? But sometimes you may want to question whether or not you're asking the right questions. That can make a big difference in how good a student you are. Many of those questions actually are biased towards an incorrect view of motion. If we take a look at a soccer ball, does it make sense to say that the soccer ball is naturally in a state of motion, or naturally at a state of rest? Aristotle's views on matter go back to, like I said, something like 300 BC, and he was an excellent thinker. I've read some of his work. It's just wonderful, logical stuff. But when it comes to doing science, he really couldn't be considered a scientist. He was more of a philosopher. He made two classifications, though, when it came to matter. He divided matter into natural motion and violent motion. In his view, there were certain things that he thought were naturally moving. That's the way they were. Other things had to be put into motion. That second class he called violent motion. Later, in the early 1600s, thereabouts, Galileo took a more scientific approach to defining motion, and he argued that only when friction is present, as it usually is, and we talked about that on the first slide, is then when a force is needed to keep an object moving. Otherwise, objects tend to just keep moving. He used the following reasoning. Experiments that he did showed that when you take a ball and you roll it down a hill, it will roll up another hill in such a way so it'll never go past its initial starting point in terms of height. If you extend the ramp out a little bit, same thing, the ball will come to a position never exceeding the initial height. Actually, it never quite reaches that height because of friction. In his mind, he thought about, though, what if there wasn't any friction? He felt that the ball would continue to raise up to that spot and no further. But what if we extend that ramp indefinitely? If we extend it indefinitely, he reasoned, the ball would never stop. And so Galileo stated that there's a tendency of moving objects to keep moving. That is a natural law. And this state of motion is, or this property rather that objects have, is called inertia. Newton came into the picture and introduced some laws of motion. One of his laws, the first law, is called the law of inertia, and it is this law that we study in this chapter. Newton's first law states that every object continues in a state of rest or in uniform speed in a straight line unless acted upon by a net force. Objects in static equilibrium will remain in static equilibrium. Objects in dynamic equilibrium will remain in dynamic equilibrium unless a net force acts on them. All right? Only a force can cause change. If you introduce a force, as we did in the previous lesson with that little 7th grade girl, then you can get change to occur. So that can bring rise to all sorts of surprising sorts of things. Here, this classic demonstration of pulling the tablecloth out from underneath some dishes is a reality. You can actually do this. It is very tricky because friction can impart a force onto those dishes. So I guess I wouldn't recommend you go and try it, because there are some little ways in which one must go about doing it to make sure that it does work, but it is possible. So objects in rest will stay in rest, objects in motion will stay in motion. Both of these are exhibiting inertia. Mass comes into the picture when we try to quantify, or in other words, put a number to the amount of inertia something has. The more mass an object has, the greater its inertia, and the more force it takes to change its state of motion. We sort of saw this in the first lesson when we started to introduce other things like the accountant or the refrigerator. Those things had more mass, and when we used the same force, we found that we couldn't change them as much as we could with the 7th grade girl. Mass, inertia, the two are linked. You can kick a can with nothing in it and it'll go flying. But if you have some sand in it, or if it's full of some kind of beverage, you're going to find that you might hurt your foot. It's not going to want to go. It's going to want to stay at rest. Let's not confuse mass with other things. Here's an example of where some students confuse mass with, say, volume. These two things here, the pillow and the battery, have very different volumes and very different masses. The pillow doesn't have very much mass, but what mass it has is all spread out. So it has a lot of volume, but not very much mass. The battery, on the other hand, has all of its matter concentrated into one smaller little box. A lot of mass, not that much volume. Another thing that people confuse mass with is weight. Weight is a force. Gravity pulls on things with a force, and that force we call weight. So 1 kilogram of nails is a way of measuring mass. Okay? Kilograms is the unit we use. But that would have a certain weight here on Earth, and so we can easily convert between the two, but they are different things. Weight is different. Mass is another thing. If you're out in space, we would say you would experience weightlessness, but you'd still have mass. Your mass wouldn't change. If you tried to shake this rock or whatever, you'd find that that would still be just as difficult on Earth as it is out in space, because objects, once they're moving, they don't want to stop moving. And so as you try to shake that object, it's in motion, it wants to stay in motion, and now you're putting force to get it going the other way. That would be the same as it would be here on Earth. Let's do a question here and then we'll conclude. Does a 2 kilogram bunch of bananas have twice as much mass as inertia? Have twice as much inertia as a 1 kilogram loaf of bread? Twice as much mass? Twice as much volume? Twice as much weight when weighed in the same location? Think about that. Well, kilograms measures mass, and mass, we said, is a measure of inertia. So it would have twice as much inertia as a 1 kilogram loaf of bread, that the 2 kilogram of bananas would. It would have twice as much mass. But it wouldn't have necessarily the same, twice as much volume. In fact, the bananas probably would take up less space. The weight depends on where you weigh it. If you weigh it on Earth, both times, if you're comparing the bananas and the bread on Earth, then yes. If you compare the bananas as they would be on Earth to the bread on the moon, then no. Weight can change. These are some important topics. I've got some questions for you to look at after you finish watching this. You should take the quiz. Thank you.